Oh, wow. Hello, everyone. Did you manage to open the latest assignment on physics? Momentum. Did you manage to have a look? Okay. Good. So it's there. It's visible. Let's start. So today we're going to talk about momentum and impulse. And they're very similar things. And actually, in some languages, you use the same word, impulse, for both. It turns out that in English language, you use the two different words, but that's fine. So momentum is a vector quantity. That means it has a direction. Momentum is simply, momentum is defined. Oh, let's not do red. Momentum is mass multiplied by the velocity. Now, because mass is a scalar and velocity is a vector, momentum is also a vector. So velocity is a vector, that means momentum is also a vector, whereas mass is a scalar. And you can guess that the unit of measurement is kilogram meter per second. And mass is kilograms, of course, and velocity is meters per second. And yeah, so it's pretty straightforward, like the definition. What is momentum? Well, momentum is also known as the amount of motion. Okay, because talking about speed is not enough. You want to also know how much mass is moving. Another useful way of thinking about momentum is how difficult it is to stop something. Okay. How difficult momentum is the unstoppability. Stoppability of an object. So there are two ways. Either the object is very heavy and it's difficult to stop, yeah, like a truck, or it's very fast, like a bullet, and it's difficult to stop because it's moving fast. So yeah, that's the idea. Okay, so let's just calculate momentum in each case. The plus indicates positive direction. So yeah, it's a vector in the positive direction. So the momentum is going to be plus 9 kilogram meter per second. Or technically you put 9.0 because the data is given to 2 sig figs. So here you would write 9.0. If it's 1.6 times 3.4, 1.6 times 3.4, it's going to be plus 5. Minus 5 point. Now, if you do it in a calculator, it's 5.44, but your data is 2 sig figs, so it's 5.4 kilogram meter per second. That means it's in the negative direction. So in any problem, you choose a positive direction, and hence you have a negative direction. So that's what it is about. 50 grams, 2.5 east. So we convert that to kilograms, 0.05. 0.005 times 2.5. It's going to be 0.13 east kilogram meters per second. If it's 120 kilograms and it's stationary, the momentum is 0 kilogram meters per second. 0 doesn't really have a direction, so it's any direction. and all the directions at the same time. Does that make sense? Do I need to explain anything more? Are you 100%? Yes, give me a score out of 10, please. Momentum. Out of 10. Good. Okay, I got 4 out of 5. Good enough. Now, this is what momentum is. Now, impulse is simply the change in momentum. Impulse is the change in momentum. So imagine a 2 kilogram mass was moving east at 12 meters per second. Now it is moving west at 6 meters per second. Now it is important that the direction has changed. Okay, so before it is before, so let's say it was east is positive. Say east is positive and west is negative. Before it was plus 12 meters per second. Therefore, the momentum before was 2 times 12, which is 24 kilogram meters per second. After, the velocity is minus 6 meters per second. So momentum after is 2 times negative 6, which is negative 12 kilogram meters per second. Right, because it's moving in the opposite direction. So the change in momentum, so the impulse is simply the change in momentum, which is momentum after minus momentum before, which is minus 12 minus 24, which is negative 36 kilogram meters per second. Any questions here? Does everyone understand what I'm talking about? Impulse is the change in momentum. Please ask if you're not clear. Oh, that's fine. That's fine, Mark. You can always watch the webinars in recording. Okay. Now, it turns out that, and we show this in the assignment, that change in momentum is also the resultant force multiplied by the time. That's why I call it impulse of a force. Impulse of a force is simply the force multiplied by the time for which it is acting. So if I take an object, this brick, and I apply a force to it, I will change the momentum of that brick. It's not a brick, it is a brick because it's stopped working. Anyways, I apply a force and it changes momentum. Just like the same way I apply a force and it changes kinetic energy. but this is a slightly different thing. It's momentum. Kinetic energy is a scalar. Momentum is a vector. So a 5 kilogram trolley is moving at 3.5 meters per second west. A 12.4 newtons force east acts for 3.5 seconds. Take traveling east as being positive, and traveling west as being negative. What is the acceleration? So east is positive. So acceleration, we know that acceleration is force divided by the mass from Newton's second law. Specific impulse in rocketry refers to how long it's not how long. Specific also always refers to per kilogram. So the word specific in physics means per kilogram. Specific means per kilogram. So specific impulse, I'm guessing, I'm not familiar with the term, but I'm guessing it means the impulse delivered by 1 kilogram of fuel, which is a very useful thing. You want to know the final momentum of the rocket. You want to know how fast you're going. So you know how much fuel to put in, right? So that would make sense. Acceleration is force divided by mass. So, force divided by mass, so it's 12.4. So it's plus 12.4 because it's east. 0.4 divided by mass, which is 5 kilograms, which is 22.48. 12.4 divided by 5. 2.48, indeed. Plus 2.48 meters per second squared, and the direction is east. Acceleration is east because the force is east. Velocity change. Well, we know the acceleration, the velocity change. We know that acceleration is delta v divided by delta t. That means delta v is acceleration multiplied by delta t. So 2.48 times 3.5. 2.48 times 3.5 times 3.5. That gives you 8.68 meters per second. That's the change in velocity. What's the original momentum? Well, the original momentum was 3.5 times 5. Initial momentum is 3.5 times 5. Well, it was traveling west, so it's minus 3.5 times 5. 0.5 times 5, I'm guessing that's 17.5. So negative 17.5 kilogram meters per second. So it was moving that way, and the momentum was minus 17.5. The new momentum, so it was moving at 3.5, and now the velocity changed. The velocity, the final velocity is the initial velocity plus the change in velocity. So the initial velocity is minus 3.5 plus the change 8.68, which is 5.18 meters per second. That's the final velocity. So the final momentum is the velocity. Yes, the final velocity times the mass. So it's 5 multiplied by 5.18, which is 5 multiplied by 5.18, 25.9 kilogram meters per second. What's the change in momentum? The change in momentum is the final momentum minus the initial momentum. So final momentum is 25.9, 25.9 minus the initial, minus minus 17.5. So 25.9 minus, well, plus 17.5. 43.3. So it's 43.4 kilogram meters per second. That's the change in momentum. What's the product of force and time? Okay, force multiplied by time. So force is 12.4 times time, 3.5. 12.4 times 3.5, which is also 43.4. Now it's Newton seconds, because it's newtons times seconds, although it is the same thing. Kilogram meters per second in Newton seconds is the same thing. So you can see that indeed this equation holds. The change in momentum is force multiplied by time. Okay, so it makes perfect sense. We can also prove that, but it's done in the assignment. The proof of this formula is in the assignment, so I'm not going to do that. Any questions here? Do you fully understand every part? Can I get an answer from everyone, please? There's 6 of you. I only saw problem 7. Oh, what do you mean? I'm not sure what you mean. Okay. Yeah. Luke, Mark, Anne, Vishaka, what about you? Parachita, do you understand? Oh, yes, Parachita, yes. Okay. All right. So we're talking about, once again, we're talking about two things. Because of momentum, and we're talking about impulse. Impulse is the change in momentum. And impulse is also force times the time. Okay, what magnitude of the force is needed to accelerate 300,000 kilogram wide body jet from 0 to 90 meters per second in 50 seconds? That sounds about right. When a plane takes off, it takes about 50 seconds. So, so it's a wide body jet. Does anyone know how many wide body jets are currently in production? It's not too many. No, there's at least 3. I can think of 3. The 777, the 787, and the 350. Oh, 330, of course, and 330, so 4. So 330, 350, 787, and 777. I think that's it. They are twin aisle. Twin aisle, that means wide body. Okay. And we're looking forward to the 929, which is they're going to be the fifth one production. Okay, so all right, so 300,000 wide body jet. So from 0 meters per second to 90 meters per second. So the initial velocity is 0. Well, you can write that. The initial velocity is 0. The final velocity is 90. The mass is 300,000. So the initial momentum is 0 multiplied by 300,000, which is 0. The final momentum is 300,000 times 90, which is something ridiculously big. 90 times 2. 90 times 300,000. 27 million. 27. Well, 2.7 times 10 to the 7 kilogram meters per second. So the force is well, we have force multiplied by time is the change in momentum. So force is the change in momentum divided by change in time. So the change in momentum is the final minus the initial divided by the time, which is 2.7 times 10 to the 7 minus 0. We're divided by the 50 seconds, and that is divided by 50. 540,000 newtons. Let's take a sanity check. What's the most powerful engine? I think it's 30 tons of force. So yeah, that's a very reasonable. They're very reasonable answer. So yeah, that's approximately the force needed. Okay. So is everything clear on that? So we have a force, we have time, we can work out force times time gives us the change in momentum. Yeah. Okay. And now we are talking about systems of objects. That means more than one object in a system. And the topic is conservation of momentum now. And then conservation of momentum. It turns out that if you have a system of objects with no external forces, the total momentum of all the objects is a constant value. Conservation of momentum. In an isolated system, the total momentum remains constant. What does that mean? Well, that means that the total momentum before before what? Before an event. Usually it's a collision. Yeah, total momentum before, let's say collision, explosion, or interaction. total momentum before interaction is equal to the total just a second. Is equal to the total momentum after the collision, explosion, interaction, whatever that is. The total momentum before is equal to the total momentum after. So these trolleys collide, and the conservation of momentum tells us that the total momentum before is equal to the total momentum after. What does an isolated system mean? An isolated system means that if there are no external forces, or the external forces are balanced. So in this case, there's the weight acting on the trolleys, but there's also the normal reaction which counteracts that force. So we can say that the external forces are balanced. So unless there's a lot of friction here, we can say this is an isolated system. Now, two 2 kilogram trolleys collide and stick together. They collide and stick together on a smooth horizontal surface. So smooth means no friction. One trolley is at rest before the collision, and the other is initially at 20 centimeters per second, as shown in the figure. Calculate the combined velocity of the trolleys after the collision. So what we need is we need a before and after. So before, after. So before, this trolley is moving, this is stationary. So the momentum, the total momentum, is the momentum of this trolley. What's the momentum of this trolley? Zero 0.4, indeed, because the speed is 0.2 meters per second, 20 centimeters per second, 0.2 meters a second. And so 2 times 0.2, and this is 0.4 kilogram meters per second. Now this one, well, it's 2 kilograms, but it's not moving, it's 0 meters a second. So plus 0. So the total momentum is 0.4 kilogram meters per second. That's the total momentum of the two trolleys before they collide. Now, once they collide, they are now moving together. And their combined mass is 4 kilograms. And they are moving with an unknown velocity. Let's call it v. So the total momentum is 4 multiplied by v. Now, conservation of momentum tells us that these two should be the same. So this has to be the same as this. So we can write this down. So total before is equal to the momentum total after. So 0.4 equals 4 times v. So v is equal to 0.1 meters per second. That's it. So it is moving there. Well, after they stick together, the final velocity v final is 0.1 meters per second. And it kind of makes perfect sense. It is moving at 20 centimeters per second. And the mass is 2 kilograms. Now the mass becomes 4 kilograms. That means the speed becomes 10. Next, problem 5. Two trolleys are at rest and in contact on a smooth, level surface. A coiled spring in one trolley is relaxed so that they explode apart. The lighter trolley moves at 550 centimeters a second. Calculate the speed of the other trolley. Okay, so we have two trolleys. And effectively what we have is a loaded spring. It's a spring between them. Once the spring is released, they start moving in opposite directions. So this moves and this moves. So this is 2 kilograms, this is 5 kilograms. Let's say this moves with velocity v1 and this moves with velocity v2. Okay. So we know that this moves at 50. Now it's moving to the left, so we can use that as negative. So before they were not moving. So the impulse, the total impulse before is equal to 0. Total after is equal to, so minus v1 times 2 plus v2 times 5. And because they are the same, they have to be equal to each other. So minus 2v1 plus 5v2 is equal to 0. But v1 is 50 centimeters a second. So minus 2 times 50 plus 5v2 is 0. So 5v2 is equal to 100. So v2 is equal to 20 centimeters a second. We need to remember that we use centimeters a second, so we're going to get centimeters a second. That's it. It's moving at 20 is 20 centimeters a second. Let's just calculate the momentum. So after the collision, after explosion. We call it explosion because we have two objects which were stationary and now they're moving apart. Even though it doesn't look like an explosion, we still, in physics, we call it an explosion. Okay. After the explosion, momentum of the first trolley, it's minus 50 times 2. Minus 0.5 times 2. That's minus 1 kilogram meter per second. The second trolley is 0.2 times 5, which is 1 kilogram meter per second. So you can see the momentum of the first trolley is minus 1, the momentum of the second trolley is 1. Yes, they have the same momentum, but in opposite directions, which makes perfect sense. Energy stored. How much energy was stored in the spring? Well, where does the system get energy? Well, it gets energy from the spring. How much energy was stored? Well, we need to find the kinetic energy of the first. So kinetic energy of the first trolley is 1/2 multiplied by 2 multiplied by 0.5 squared. And that is 1 times 0.25 joules. Kinetic energy of the second trolley is 1/2 times 5 multiplied by 0.2 squared, which I believe to be 0.1. Let me double check. 0.2 squared. So 5 times 0.2 is 1. 0.2, 0.2, yes, 0.1 joule. Interesting. The heavier trolley has the same momentum, but it has smaller energy. And that is always the case. In any explosion, the heavier here chunk will have less kinetic energy. It's quite interesting because if you think about it, it has to be that way. Imagine you're shooting from a rifle. That's an explosion. That's a literal explosion. You're shooting from a rifle and you have a bullet. Now, when the bullet is shot forward, the rifle has a recoil. There's a recoil velocity. I've never held a rifle. No, I've never shot from a rifle. I held a old, like a 17th century rifle, but that's about it. And but I can imagine the force that you feel if you're shooting it. Feel a force backwards. That's the recoil. And according to conservation of momentum, the bullet and the gun have to have the same momentum, right? Because before explosion, the total momentum is 0 because they're both stationary inside the barrel. Now, after explosion, of the gun plus the momentum of the bullet have to equal to 0 as well. That means the velocity of the gun is minus the momentum of the bullet. Effectively, what am I saying? They have the same momentum. However, because the rifle is much heavier, it has a much smaller kinetic energy. Kinetic energy of the rifle is much smaller than the kinetic energy of the bullet. I don't want to spend time proving that. An interesting thing. Take a for instance. And I think we don't have this problem, but if let's say so, the kinetic energy of the bullet divided by the kinetic energy of the gun is equal to the mass of the gun divided by mass of the bullet. So that means if the gun is 100 times heavier than the bullet will have 100 times more kinetic energy. If gun is 100 times heavier, the bullet will have 100 times more kinetic energy. And that makes sense because you want the bullet to have a lot of energy, and you definitely don't want the gun to have the same amount of energy, right? Otherwise, you could only use it once. Okay, make sense? Any questions? Minus 20. Yeah, would be correct as well. Depends on which direction you choose as positive. You could say that this is positive, then this would be minus 20, or V2 is minus 0.2 meters per second. So both answers are valid, but it depends. Okay, now we're getting to much meatier problems, okay? A bullet of mass 9 grams is hitting a pendulum of mass 3 kilograms. So it's a pendulum. And there's a bullet. And it hits the pendulum, and the pendulum starts to swing. Makes sense, right? If a bullet hits a pendulum, the bullet starts swinging. This is how the speed of bullets are measured, as a matter of fact. And it's called a ballistic pendulum. Ballistic pendulum. This is like a model. So you shoot a pellet. In this particular case, you shoot a pellet. It gets stuck into the in the pendulum, and then it deflects at a certain angle. And I think this thing is designed to stop at the maximum angle. So it has some friction, and it allows you to see the maximum angle of maximum angle. Okay. So there are two things going on here. First of all, you have conservation of momentum when you hit. Okay, so let's see. This is a 3 kilogram, and this mass is 9 grams, so 0.009 kilograms. Now it's traveling at 300 meters a second. We want to know how fast it will move. So before, the momentum before is 0.009 times 300 plus 0, because this is not moving, which makes it 0.009 times 300, 2.7 kilogram meters per second. Momentum after. Well, the mass is 3 kilograms. Well, it's not 3, it's 3 kilograms and 9 grams. 3 kilograms and 9 grams, because the bullet gets stuck in the pendulum. Multiplied by the velocity, which is unknown, but it also has to equal to 2.7 kilogram meters per second. And from here, we can work out 3 times 0.009 V equals 2.7. So V is divided by 3.009. So 0.897. 0.897 meters per second. So that's the velocity. So once you shoot the bullet and it gets stuck in the pendulum would move off with a velocity of 0.897. And the question is, calculate the increase in height. So basically, calculate the height at which the maximum height of the pendulum. What can we use here? How can we calculate the maximum height? What do we, which principle do we use here? Yes, everyone's on board? So you have a moving object. You want to know how high it will rise. Of course, it's conservation of energy. So 1/2 mv squared is equal to mgh. Mass cancels, and you have h is equal to v squared divided by 2g, and that's 0.897 squared divided by 2 times 10. And this is 0.04 centimeters. Oh, sorry, meters. Meters, which is 4 centimeters. So it will rise by 4 centimeters. And if you know the length of the pendulum, you can work out the angle as well. You'll have a problem like this. And if you know the angle, you can also calculate this distance, x, which is the amplitude. Amplitudes. Okay, so if the length of the pendulum is L and it deflects by angle theta, so this length is L cos theta. So H would be L minus L cos theta. Okay, so you can work out theta from here. And if you want to know the horizontal displacement, x is the amplitude, is going to be L multiplied by sine theta. Also a useful thing to do. So I kind of given away pretty much the whole solution to the question in the assignment, but it's a difficult question. Right, a puck sliding down a non-fixed wedge of mass m. So imagine you have a wedge, and there's a puck here, mass m, and the wedge is mass m. And this height is h. What would happen? What would happen if we release? And this is a smooth table. What would happen if we release the puck? Yeah, the puck will move that way, and the wedge will move that way. Absolutely. Well, this is caused by the normal reaction force. If you think about the normal reaction force pushes the normal reaction force pushes the puck that way, but there's an equal and opposite force pushing that way, also a reaction force. So this force pushes the wedge to the right, and this force pushes the puck to the left. So you have mass times velocity of the puck is equal to mass times the velocity, let's call it u, and this is v. Well, after it moves off with the velocity v. We don't use that here. Mu, they have the same momentum. But now, where does the energy come from? Well, the energy comes from the gravitational potential energy. So gravitational potential energy of the puck at the beginning has to equal to the kinetic energy of the puck plus kinetic energy of the wedge. So you would have gravitational potential, so mgh equals kinetic energy of the puck 1/2 mv squared plus 1/2 m capital M u squared. And you have this equation and then this equation, and you can solve the two equations for whatever value you need. That's it. It's one of the examples. Okay, so it's one of the examples in the assignment, so I won't spend too much time going through that. But yeah, it has to have a conservation of momentum. So if the puck moves to the left, the wedge has to move to the right. Now, if the wedge was fixed to the table, that would not be an isolated system because there would be an external force holding the wedge. As long as there's no friction, it's an isolated system. But if the wedge was fixed, there would be an external force, the force that is holding the wedge. I hope that makes sense. Conservation of momentum in 2 dimensions. That's an interesting one. Suppose you have a puck, a hockey, let's say 2D. Oh, why would we use a puck? Let's do snooker. Snooker balls. Position. That's not. It's definitely not what I wanted to do. Yeah, that's a bit of a useless thing. Okay. Let's say we have a ball and it is hitting another ball. Let's make it a different color. So let's say the red ball is moving with velocity u, and then it hits the blue ball. As you can see, the contact point is here. That means there's a normal force between them. It's pushing this ball this way and this ball this way. As a result of that force, the blue ball starts to move in the direction of that force. So this is V2. Let's call it V2. And U, it experiences a force that causes it to change the direction. Now, the red ball moves somewhat like this. V1. Okay. So conservation of momentum is a vector. So conservation of momentum. So if the mass of the ball is m, so mu is equal to mv1 plus mv2. And actually, you could cancel the m's because they have the same mass. So u, velocity, initial velocity, is the final velocity plus final velocity of the second ball. An interesting thing. Interesting idea. So what you have is you have the momentum of the first ball, P initial, and then you have two momenta this way and this way. Let's call it P2 and P1, and these are vectors. So conservation of momentum tells us that P1 plus P2 has to equal to P initial. Right? It's a triangle rule for adding vectors. P initial is P1 plus P2. So total momentum is conserved. Total momentum is conserved. Okay? Is that making sense? Now, for snooker balls, you can assume that the kinetic energy is conserved. Collision is elastic. Collision is elastic. Means kinetic energy is conserved. And that means we have kinetic energy before initial equals kinetic energy of the first ball plus kinetic energy of the second ball. And if you write this down, 1/2 mu squared, yeah, equals 1/2 mv1 squared plus 1/2 mv2 squared. And as you can see that 1/2 mv cancel, and we have u squared equals v1 squared plus v2 squared. Interesting. So if we take u, and this is v1, and this is v2, and somebody just told us that u squared is v1 squared plus v2 squared. What kind of triangle is that? It's a right angle triangle, indeed. Pythagoras theorem, this is 90 degrees. So, in an elastic collision between, in an elastic collision, two snooker balls will always, two objects of the same mass will always leave at a 90-degree angle. So, consequence in an elastic collision, two objects of equal mass, two smooth object equal mass will travel at right angles. let's also talk about like something more pragmatic. So if you know, if you have a ball that is traveling, let's say a 1 kilogram ball traveling at 3 meters a second, and then you have another ball and another ball. Let's say this is a 2 kilogram ball, and this is a 1 kilo, and this is the same 1 kilogram ball. So this is ball A, this is ball A, and this is ball B. Now, 1 kilogram. And let's say this angle is 30 degrees, and this is 2 meters a second. Okay. So what do we do here? What can we do? We say that we have two momentum. We have the horizontal momentum is conserved and the vertical momentum is conserved. So horizontally, the momentum before, that's 1 times 3. 1 times 3 is the total momentum, is equal to, well, 1 for this ball, 1 times cos 30 degrees. That's the horizontal momentum of ball A. Horizontal momentum of ball A. So this is 2 cos 30. This is 2 sine 30. Now this ball, we don't know the angle and we don't know the speed. So let's call the angle theta. So it's going to be plus v cos theta. Now vertically, we can say that the momentum, this vertical momentum, so vertically momentum is conserved. So initially there's 0 vertical momentum, and that's equal to the vertical momentum. So 2 times 2 sine 30 minus, sorry, 1 times 2 times 30 times 2 times v sine theta. And from here, we can work out v and we can work out sine theta. So cos 30, that's square root of 3 over 2. So v cos theta equals 3 minus square root of 3 over 2. 3 minus, well, 3 minus cos 30, which is 3 minus 3 over 2, which is 2.133. 2.133. And v sine theta, from here we can work out that it is 0.5. Now you can divide them together. So if you divide the two vectors, so v sine theta divided by v cos theta, v cancels, and that's equal to 0.5 divided by 2.133. So tan theta is equal to 0.5 divided by answer, which is 0.234. So theta is in arctan, inverse tan of 0.234, which is 13 degrees. 13 degrees. We can work out the angle. The angle is 13 degrees. And then we can work out v. If we know the angle, we can work out v from here. That's fine. Does that make sense? I mean, it is quite a difficult problem. But the idea is that you can do it in 2 dimensions. You have to just do it in 2 dimensions separately, and that's it. You do the horizontal, then you do the vertical. Momentum has to be conserved in any direction. Momentum is conserved in any direction. Let me write this down in big letters. Momentum is conserved in any direction. Lovely. And finally, a topic that I really enjoy is called the kinetic energy paradox. So let's have a look. When we did Newton's laws, we discussed that there are inertial frames of reference and they are indistinguishable from one another. Right? The inertial frames of reference are all the same, and the laws of physics are the same in any reference frame. Cool. So let's consider this example. We know the work energy principle. We know that the work done is equal to the change in kinetic energy. That's the work energy principle. Let's say we have a car and it's stationary. Let's say for simplicity, and it starts to accelerate. This car starts to accelerate and it reaches 20 meters per second. Meters per second. So 0 meters per second. This is 20 meters a second. Okay. Fine so far. Let's take the mass. The mass of the car, let's let it be 1,000 kilograms. So the change in kinetic energy of the car is 1/2 mv squared, which is 0.5 times 1,000 times 400, which is something like 200,000 joules. Is that it? Does that sound right? 0.5 times 1,000 times 20 squared, 200,000 joules. Okay. Lovely. So the engine needs the work done by the engine. Done by engine is 200,000 joules. So energy in fuel, useful for energy in the fuel is 200,000 joules, right? Because that's where the energy is coming from. All right, is everyone on board so far? Never going to lose a snooker game with a protractor. Lovely. Use energy fuel. Okay. Because we are converting fuel into movement, right? So we have the fuel, there's energy in the fuel, we use it to accelerate the car. Makes perfect sense. Now, imagine that you are not stationary. Imagine you are in the passenger seat of another car, which is moving at 20 meters a second. Now, imagine you are sitting in a car traveling in the opposite direction. Now, in your frame of reference, you are in an inertial frame of reference. That means laws of physics apply to you as well, in the same way as they apply to it. So Newton's laws work. Basically, you are traveling at a constant velocity, therefore it is an inertial reference frame, and therefore Newton's laws work. Newton's laws are true. We also know that the change in kinetic energy is equal to the work done. And where does the work come from? Well, work comes from the fuel. Now, from your point of view, initially, the car, let's call it car A, and this is car B. Initially, car A was moving at 20 meters per second. So it wasn't stationary because you were moving, so the other car was moving towards you, right? So if you are in your reference frame, you are stationary in the car and the other car is moving towards you, right? Was moving and it accelerated to 40 meters a second. So this effectively, from your point of view, the car doesn't go from 0 to 20, the car goes from 20 to 40. Does everyone understand this? Do I need to explain this better? From your point of view, the car goes from 20 to 40, not from 0 to 20. So for a stationary observer, car A goes from 0 to 20 meters a second. For an observer in car B, sorry, we've got a visitor. Hello. She likes cars. Okay, for observer in car B, car A goes from 20 to 40. Now, sorry. So how much energy do you need to go from 20 to 40? That's the thing. So change in kinetic energy is equal to the kinetic energy before, so it's 1/2 times 1000 times 40 squared minus 1/2 times 1000 times 20 squared. And that, so minus 0.5 times 1000 times 40 squared, and that is 600,000 joules. So from your point of view, engine does 600,000 joules of work, and the fuel had 600,000 joules of energy, which sounds like nonsense, because how can the fuel in car A suddenly have more energy just because you are moving? Okay. Do you understand the issue here? To go from 0 to 20, you only need 200,000 joules of energy, but to go from 20 to 40, you need 600,000 joules of energy. Well, it makes sense that it doesn't make sense, right? Suddenly, that's why it's called a paradox. So observing it from a different angle suddenly changes the whole thing. Now we say that kinetic energy is frame dependent. So the kinetic energy depends on the frame of reference. Yes, it does, but why? Let's try to explain that. So what's actually going on? So the explanation, one of the explanations is as follows. Explanation. Because you cannot take a car. It's not a car in a vacuum. Okay. It's not a car in a vacuum. This car A, it's on the ground. And the ground is on the planet Earth. So this is Earth. So as the car accelerates to the right, the planet Earth accelerates to the left. It has to. Well, maybe not the whole Earth, but little parts of Earth. But overall, there is a shift in the Earth. Actually, the Earth changes shape slightly because of the car. So the car pushes forward, so the Earth has to move backwards. But in this frame of reference, the if remember, the change in kinetic energy of the Earth is like almost zero. So the change in kinetic energy of the Earth is the mass of the car divided by the mass of the Earth multiplied by the kinetic energy, by changing kinetic energy of the car. Which is approximately 10 to the minus 21 joules, which is nothing. Right, so it's literally zero. So the change in the Earth doesn't change. The change in kinetic energy of the Earth is minuscule. Because the Earth is stationary. The Earth is stationary. The car is stationary. The car moves forward. The Earth moves backwards. But the kinetic energy of the car is going to be of the Earth is going to be zero. Okay. But if you now go into the frame of reference of the other car, now the car is moving at 20 towards you, and the Earth is moving at 20 towards you. And after some time, this car moves towards you at a speed of 40, but the car is moving towards you with a speed of 20 minus u, because the Earth slows down a little bit as a result. Because the car accelerates towards you, that has to cause the Earth to slow down. Because you're in the car, the Earth is moving towards you. And because there's a change in kinetic energy, the change in kinetic energy of the Earth, this change in speed is very small, but because the Earth is so massive, the change in kinetic energy is not minuscule. It's actually 400,000 joules in your frame of reference. So in your frame of reference, the Earth has lost 400,000 joules of energy. Sorry, yeah, and now, well, minus 400,000, and that resolves the paradox. Because remember, going from 20 to 40, going from 20 to 40 requires more energy to go from than to go from 0 to 20. Yes. So in this case, the Earth goes from 0 to 0.000000000 21 zeros 1. Yeah. But here, Earth goes from 20 to 19.999999999999921 nines. Even though the change in speed is the same, but the change in energy is very, very different. Okay, so as an exercise, calculate the change in kinetic energy if mass is 10 to the 24 kilograms and velocity goes from 20 to 20 minus 10 to the power 21 minus 21. So this is the initial velocity, this is the final velocity, which is very close. Actually, you know what? Zero 0.5 times 10 to the power 4 times 20 minus 0 0.5 times 10 to 10 to the 24 times open bracket 20 minus 10 to the power 21. Oh, I forgot to square it. Square it. Oh. Okay, something went wrong. I don't have a good answer. My answer is ridiculously large, but hopefully, anyways, does it make sense to you? Does it make sense? Oh well, people have left. All right. Yeah, okay, that's fine. I'll see you next week then. Welcome.